This common phenomenon can be seen in your kitchen sink. The water appears to spread out in a thin, even layer until reaching a boundary where it suddenly becomes deeper and more turbulent. This is known as hydraulic jump. Understanding this phenomenon on a larger scale is vital to engineers. Controlling fluid flow is one of the main aims and challenges of modern infrastructure. Irrigation canals, stormwater drainage facilities, and aqueducts, to name a few. Within renewable energy, engineers need to be able to predict how a fluid will behave in order to design structures that will generate the desired output whilst maintaining a long lifetime. The study of how water with a free surface behaves that's not confined within a pipe is called open channel hydraulics. To understand the hydraulic jump phenomenon, as shown in the kitchen sink, you must first consider sub- and supercritical flow. This is Froude's equation. The Froude number is a dimensionless number which defines the flow regime of open channel flow, whether it's sub- or supercritical flow. It's the ratio of inertial and gravitational forces, with v being the velocity, g the acceleration due to gravity, and h the main depth. The Froude number is relevant in fluid dynamic problems where the weight or gravitational force of a fluid is an important force. It's important when analysing surface behaviour, free surfaces like cold windows and hot radiators, or open channel flow in open conduits like water channels, sewer pipes, spillways, weirs, channel flows, rivers, and even in ship design. Water measurement in an open channel flow generally requires the Froude number to be less than 0.5 to prevent waves disturbing accurate head readings. When the Froude number is 1, the flow is said to be critical and the velocity is equal to the velocity of wave propagation, and downstream waves or pressure disturbances cannot travel upstream. This sounds complicated, but we see it all the time and it's very easy to understand once demonstrated. Slow tranquil flow conditions, or flows with a Froude number less than 1, are called subcritical. In this case, the wave speed is faster than the flow velocity, and if you were to drop a small object in the water, the ripples or waves this will create can travel against the flow direction. A fast-moving flow, or one with a Froude number higher than 1, is called a supercritical flow. The flow velocity is faster than the wave speed, and when dropping a small object in, the ripples or waves cannot move back against the flow. A flow profile can naturally transition from slow to fast, or from subcritical to supercritical. For example, a steep slope or cliff. Here the Froude number will move from below to above 1. When the opposite happens, the Froude number moves from above to below 1, and the flow moves from super to subcritical flow, or from fast to slow. Something interesting occurs: a hydraulic jump. In this experiment, a hydraulic jump can be manufactured using a sloped open channel flow. The circulating water has been dyed so the phenomenon can be seen more clearly. The sink demonstration happens due to surface tension and not gravity. However, in this example, gravity is influencing the hydraulic jump. Opening the upstream gate a little creates a fast supercritical flow, and obstructing the area downstream forces a transition into a slow subcritical flow near the bottom. Right where the flow transitions from super to subcritical, you can clearly see the hydraulic jump. Naturally, this happens in steep mountain streams, where supercritical flow crashes into rocks, changing direction and transitioning to a slower subcritical flow, creating whitewater turbulence and the occasional hydraulic jump. Another example is tidal bores. These occur when an incoming tide forms a wave that travels upstream against a river, such as the Severn bore wave. In many of these cases, the bore travels as a moving hydraulic jump, similar to what is shown in the example. When we make releases into a spillway from a hydro turbine, the water can come down at high velocities. This supercritical flow can cause erosion and eventually lead to the failure of the structure. Most hydraulic structures will have some form of energy dissipator on the downstream end to reduce the velocity of flow and protect against erosion. There are many kinds of hydraulic energy dissipators. However, the most common types, also known as stilling basins, for large structures are designed to force a hydraulic jump. They create so much turbulence they can effectively dissipate the energy as heat. Most use different combination of blocks, slopes, and end sills to control how the hydraulic jump forms. The photo is just an example of a few variations. We've covered the Froude number as well as sub- and supercritical flows, all to understand hydraulic jump, a simple everyday phenomenon that can be seen in natural and complex engineering structures, as well as your kitchen sink.